Okay, guys. So last time we finished up our discussion relating this idea of free energy under a highly restrained set of conditions, where we were essentially disallowing pressure volume work or constant temperature pressure and whatever, but thinking about the remaining work we could do. And we related this idea to the where we're sort of headed, which is moving electrons around um, or moving them between high potential and low potential centers for the purposes of doing work, right? And that was this idea of electrical work. And we related that idea of that free energy difference and the ability to do electrical work to that fairly simple relationship of moving a particle of a given charge in an electric field, right? This sort of minus n times with the formal charge times F, Faraday's constant, and the electric field potential in volts, right? And I just want to correct us. I screwed up in the last video, which is the magnitude of Faraday's constant, which anybody could easily look up, but for completeness, it's of course 96.4 times 10 to the 3 coulombs per mole, which is what I spaced on the last time. Okay, so what we want to do now is we want to figure out a way that we could sort of relate this idea of this free energy difference to something we could actually measure, right? And as I pointed out at the beginning of this lecture, where we're headed here is in thinking about a certain type of chemistry, which we've only sort of dealt with peripherally, which is of course redox chemistry. And in redox chemistry, unlike other type or more standard organic chemistry that we've thought about it, we're explicitly dealing with the movement of electrons that are sort of more mobile in some sense than electrons in standard bonding orbitals, right? This is sort of more like electron movement in the sort of shared orbitals of a metal, for example, right? So this is, we're moving closer to something that's more like movement of electrons in a wire as we think about redox chemistry, the way we're going to be dealing with it, right? Okay, but we want to come up with a way to measure some of these ideas, right? We need a practical insight into the magnitude of these free energies, right? And so to do that, probably the easiest way to think about this is to reach back for something we started the class out with, and to point out an analogy between where we're heading here with redox chemistry and acid-base chemistry. Just as a quick reminder, you guys hopefully will recall that discussion we had about weak acids and weak bases, where we of course have a weak acid that can dissociate into a conjugate base and a proton, for example, right? And we had an associated equilibrium constant, that Ka, right? And we went through all the gyrations of defining that equilibrium constant, right, as you guys recall, as that simple ratio of the proton concentration times the conjugate base concentration divided by the conjugate acid concentration. And we then went through the gyrations of connecting this all up to the Henderson-Hasselbalch equation, right? As you guys recall, hopefully. I went through that simple derivation and we ended up with this idea that the pH, or the minus log of the hydrogen ion concentration, is just equal to the minus log of that equilibrium constant plus the log base 10 of the ratio of the conjugate base to the conjugate acid, right? Right. Okay. And so the important analogy here is this idea, sort of the pKa in this Henderson-Hasselbalch equation, right? So if you think about it, the pK gives you some idea of the sort of tendency, right, of that acid to give up a proton, right, or of a base to take up a proton. It tells you something about, the lower the pK, right, stronger an acid it's going to be. The higher the pK, the stronger a base a given weak acid is going to be, or the conjugate base is going to be, right? So that the pK magnitude of the pK alone gives you some tendency or some insight, just looking at the number, of how readily a given Bronsted acid or base is going to give up or take up proton, right? And so what we're looking for now is sort of an analogous idea with respect to redox chemistry. Okay, so to carry this analogy out a little bit further, one could then write out similar to acid-base reaction. So in a redox reaction, we of course would have something that was reduced, for example, that is then in some maybe equilibrium with something that is now more oxidized, right? Say plus an electron, sort of in a general sense. And to get a little more specific about it, but as an example, something like maybe iron 2, which is more reduced than iron 3 plus an electron, right? So that's the sort of the kind of system we're going to be thinking about here. Now, of course, electrons don't just go floating around in solution. I mean, protons really don't so much either, but electrons really don't, right? It's a fundamental particle. You can write this out conceptually this way, but this is not fundamentally how electrons are going to move between different redox centers. Transfer of an electron is fundamentally a quantum mechanical effect, right? And so you unlike with the acid-base chemistry, which you can realistically write out the way we've written it here, where there is a proton dissociation, okay, maybe it's going to be taken up as hydronium, right, in aqueous solution. You don't have electrons floating around in free solution, right? That just doesn't happen, right? Okay, so the way these sort of reactions do work in reality, however, is you have so-called redox couples, right? And a redox couple that might be relevant, say, for movement of electrons in and out of, say, iron would be something like this, maybe having copper, produced copper 1, plus iron 3, that would then see the reduced copper get oxidized by the iron 3, and the iron 3 then get reduced, right? So we would then make, as a result of that, electron transfer copper 2 plus iron 2, right? So that we basically, this would be our, in redox parlance, our reductant, right? And the iron 3 would be our oxidant, right? And on the other side of the equation, we now have our oxidized reductant, right? And our oxidant has now been reduced. So we have a reduced oxidant, right? Okay. Now, hopefully this is some aspects of this you guys recall from your undergraduate chemistry. So what we want to do now is we want to develop an approach that would let us measure and sort of quantify the tendency of one of these reactions to go in a particular direction, right? We want to figure out a way to measure where that equilibrium sits, right? Does it go more to the right, more to the left? And how do we quantify that, right? So that's our goal here. All right. So what we're ultimately looking for in making that measurement is something known as, or what we really want to know about this equilibrium, is something known as the reduction potential, right? Which is that tendency we're sort of groping for here of a given reaction, say like this iron 2 reaction, to either take up or give up electrons relative to some other redox reaction, say this copper 1, copper 2 reaction. Okay, so that's what we want to try and think about. Okay, so in that respect, we're now going to, let's just turn back to the way we would probably think about this. And so I'm going to generalize it again. Let's say we have some A moles of A, and again, we're thinking about redox couples here. A moles of A and B moles of B, and this can, by oxidation or reduction, release of or extraction of electrons. Makes C moles of C and D moles of D. Well, we know we can easily, based on everything we've talked about before, When we were thinking about simple chemical thermodynamics and chemical potential, we know we can write down an expression for this process as simply equal free energy. That process is just equal to the delta G for this process was simply equal to the standard state free energy change plus RT natural log of the concentration of the products, right, multiplied, divided by the concentration of the reactants, right, raised to the molecularity in each case, right? Okay, but remember something else from the last video, right? Where again, we're dealing here with movement of electrons, not simple chemical bond making and breaking with more tightly bound electrons like we've mostly dealt with up to this point. And so because we're dealing with a sort of the more free movement of electrons, and with analogy, the analogy I like to use to like plugging something into the wall, and that free flow of electrons, there's sort of this inherent idea that there is an electric field potential here to think about. There's an electric field potential difference between this side and this side of this reaction by virtue of the tendency of one side or the other to hold on too tightly or give up electrons, which means this free energy that we're thinking about here in the context of chemical potential, the way we've written it out, is related to something else. And it's related to what we went through before, which is that sort of electrical work potential. If there's that free energy is also directly related to the amount of electrical work that could be done by virtue of the movement of those electrons. Well, if that's true, we can relate these two free energies. They have to be equal, right? If all that's going on here, we're only allowing electrical work, then this movement of electrons in this system, as expressed in this change in chemical concentration, it's also equal to a free energy change as a result of movement of particles, charged particles in an electrostatic field, which means we can equate these two so that minus N times Faraday's constant times whatever that electric field potential is between the two parts of this reaction has to just be equal to delta G naught plus RT log of our sort of chemical species distribution ratio here, right? Right? Which is kind of cool because now if I divide the right side of this equation by NF, right, I can solve for that electric field potential, right? I can solve for the field potential that has to exist between the chemical part of this reaction, it's redox couple, that has a lot of electrons it would happily give up, and the half that has a deep sink for electrons it would really like to pull and take those up, right? So we can solve for that, right? Because that's what that epsilon value represents. So we do that, and it's really sort of easy. We end up with this delta G naught minus over NF plus RT divided by NF, natural log of our species distribution here. All right, which is great because that now gives us, right, a measurement, right, in principle for the electric field potential difference. If I knew the species distribution, I knew something about that standard state for energy, well, I know N in principle, I know F, right, because I, wrote it down. Somebody else measured it for me. Faraday measured it for me. In principle, I could calculate that electric field potential difference between the left and right side of this equation. And therefore, the amount of work in principle that field potential difference could do if I moved an electron from, say, a reductant to an oxidant. That's pretty neat, right? Only one problem. How do you measure that, right? I mean, how do you go do that? It's not immediately obvious here, though, is it? But there's a hint, right? If you think about that. Remember what this this sort of epsilon value here, as we talked about it, when I sort of went through that little demonstration of what electrical work means. This is basically an electrostatic potential, right? That's an electrostatic potential. This is in volts, right? So in principle, anybody who's ever done anything with a multimeter knows it's pretty easy to measure electrical voltage, right? Just need a circuit and a voltmeter. Turns out that's exactly what we need. We need a way to measure the electrostatic potential difference between the two halves of this reaction with a special device. And this device is known as an electrochemical cell, right? So it's worth thinking about this a little bit because it makes this a little bit less mysterious. An electrochemical cell is a measurement device that is directly analogous, again, to a pH meter, right? So you want to measure pH, you have a special meter, there's pH electrodes you can stick in a solution and measure the hydrogen ion concentration. An electrochemical cell more or less works the same way, right? Or, well, doesn't work the same way, same kind of idea. And an electrochemical cell has got sort of two halves. It's got two half cells, right? So we've got one cell here, and the two half cells are connected by a little bridge, right? And in this bridge, we basically have a semi-permeable barrier that only permits ions to flow. I'll come back to that in a second, right? And on one side of this, it's the so-called reference cell. You always have one particular type of mixture in solution, right? So this is in solution, and you have 1 molar protons, right? At 1 atmosphere hydrogen gas, right? So what's happening over here in the reference cell is, of course, this chemical reaction, or this redox reaction. H2 can, in principle, dissociate into 2 protons, right, and 2 electrons, right? Okay. But like this, it's going to be at equilibrium, nothing's going to happen, right? Okay. Well, the secret of an electrochemical cell, of course, is that you don't just have a single test tube sitting there with 1 molar protons in it and at 1 atmosphere of hydrogen gas. You, of course, have dunked into this thing a metal plate. It's usually made of a special type of metal. I can't remember off the top of my head if it's platinum or what. I should remember, but I don't. And a wire connected to that metal plate. All right, runs through a voltmeter, which then goes down into the other cell, and it's connected to another metal plate. And this second cell is sometimes known as the test cell, right? And what you put in the test cell, right, then determines which way, or I guess its tendency, to whatever reaction you put in the test cell, determines whether electrons flow this way or this way, which is, of course, what you want to know, right? The tendency of electrons based upon whatever chemical reaction is going on in the test cell will determine whether the electric field potential runs towards the reference cell or towards the test cell. For example, you wanted to say, let's say we wanted to know how readily that iron 2, iron 3 reaction gives up or takes up electrons, right? So we could say, what if, we have this simple iron 2, right, goes to iron 3 plus an electron, right? And we want to know, relative to that hydrogen test reference cell, which way that would happen, right? So in that case, you would put 1 molar iron 2. I've got this kind of small here. 1 molar iron 2 and 1 molar iron 3 in your reference cell in solution at 25 degrees, right? And you would basically read out which direction, how the electric field potential was set, whether it's positive or negative relative to that hydrogen electrode. And this is that electrical field potential you read out in a cell like this is sometimes also known as the electromotive force, or the EMF, right? And it would be in volts, right? And it turns out that for this particular chemical reaction, this iron 2, iron 3 reaction, that the, the electrons flow from, oops, the electrons in this case flow from the reference cell into the test cell, right? So in other words, the this iron 2, iron 3 redox reaction pulls electrons. It's oxidizing the reference cell and pulls electrons in that direction, right? In the direction of the test cell reaction, right? Okay. So now you can hopefully sort of get this sort of idea that all we had to do was hook these two things up together, right? Measure that electric field potential between essentially one redox reaction and another redox reaction. And out of this comes the reduction potential, right? It's the thing we were basically after when we started thinking about this. We simply measured it by permitting these two half reactions to occur near the surface of these metal plates. And again, we're thinking about electrons more readily flowing here than in standard bond making and breaking chemistry. They can, at the surface of these metal plates, give up or take up electrons. They can run through this plate. We maintain electrical neutrality through this semi-permeable um, uh, um, uh, sort of bridge, if you want to think about it. It basically allows equalizing electrostatically equalizing ion to flow, but it doesn't allow the iron 2, iron 3, or the hydrogen cell components to mix, right? But it maintains electrical neutrality. So that allows us then to measure this electrostatic potential between the two half reactions. And that electrostatic potential is directly equivalent to the thing we're after here to begin with, which is the reduction potential, right? That's the thing we were after. So this cell allows us to measure the reduction potential directly. Which is pretty neat, right? Just like in measuring pH, right? Measure these values, right, directly, right? Okay. So now every redox reaction, say like this iron 2, iron 3, is going to have associated with it a standard reduction potential, right? Just like we saw with standard free energy values, right? Delta G naught, right? We're going to have reduction potentials that are going to be referenced to some standard state, right? And that standard state reduction potential, just like we saw with, let me go back to black here, just like we saw with free energy values, that standard reduction potential is going to be referenced to some particular set of conditions, which is going to be 25 degrees Celsius, and basically everything at 1 molar concentrations, right, for similar reasons to what we saw when we talked about chemical potential, right? And by convention, the hydrogen electrode, the reaction redox couple where you got a reference to something, and by convention, the standard standard reduction potential of the standard hydrogen electrode is set equal to 0. Everything is referenced to the standard hydrogen electrode, and like I said, by convention, it's set to 0. All right, so what that means is that for any other reaction, if the standard hydrogen electrode is set to 0, and then we want to know the reduction potential, the standard reduction potential of, say, other reactions like this iron 2, iron 3 couple. We put them in an electrochemical cell and we measure that electromotive force. That tells us something about whether, relative to the standard electrode, those reactions are oxidizing or reducing, right? Because for any reaction, where the standard, with the measured standard reduction potential, um, or any reaction that essentially that donates, let's put it that way, that donates electrons to the standard hydrogen electrode, right? Under that set of conditions, right, it's basically going to be reducing the standard hydrogen electrode, in which case the reduction potential under that set of circumstances is going to be less than zero. And the bigger, the more negative that value is, the more powerful a reductant that particular redox couple is going to be, right? By the same token, any reaction that extracts electrons from the standard hydrogen electrode will have a standard reduction potential that's greater than zero, and therefore will be oxidizing the standard hydrogen electrode. And the larger, more positive that value is, the more strong an oxidant that particular couple happens to be, right? So the basic idea here is that measuring the tendency of a given redox reaction, or a given reaction to give up or remove electrons in an electrochemical cell from the standard hydrogen electrode, lets one measure the tendency of that couple to take up or give up electrons, right? And it's measured directly in volts in the strength of that particular electron removing or donation potential, right? Okay, so how do we get this, we relate this back to free energies again? All right, well, that's fairly straightforward, right? Because if we come back up here to this equation, right? Remember, right, now that we have sort of a measurement here of the reduction potential under some arbitrary set of conditions, but we've got a standard free energy value here divided by NF, right? So we can basically replace this here with the standard reduction potential, right? They're equivalent, right? The standard state free energy divided by NF is going to be equal to the standard reduction potential, for the same reason, right, that we look up here, right? So if I had delta G naught, that's going to simply be equal to minus NF E naught. Okay, that's good, because that means then the standard reduction potential is just equal to delta G naught divided by NF, right? That's cool. So I can take this equation and I can rewrite it by, again, saying that, well, the standard reduction potential is simply equal to minus delta G naught over NF. I can rewrite that expression so that the reduction potential under some arbitrary set of conditions is just equal to the standard reduction potential minus RT divided by NF log C, again, back to our, whatever our particular molecularity and species distribution happened to be. Like for that reaction I showed you above, right, which would be pretty common for many redox type reactions. And so now that's really great, because if we had a set of tables essentially that gave us the standard reduction potentials, because someone had measured it, right, under standard conditions relative to that hydrogen electrode, I could calculate the reduction potential under any arbitrary set of conditions, right? That's great. What this equation gets a name, right? This is known as the Nernst equation. right? And it's exactly now the sort of relationship we were looking for. Because again, if you look at that and remember this relative to the Henderson-Hasselbalch equation, remember we had pH equals pK plus log, oops, log, oh, come on, over HA, right? So in basic mathematical form, yeah, it's not so different, right? We've got sort of this, maybe like this referencing value here, and then we've got this, term with a logarithm in it. That's pretty good, right? So from that point of view, the standard reduction potential is completely analogous to the pK, as we just sort of talked about right here. The more negative or more positive the standard reduction potential is, the greater the tendency of a given redox couple is to withdraw electrons or to give up electrons, right, as either a reductant or an oxidant. And it turns out, if you sort of plot out the Nernst equation, you get a relationship that ought to look pretty familiar to you from thinking about the Henderson-Hasselbalch equation. So if you plot out the sort of observed electromotive force value in an electrochemical cell, and over here you're sort of at 100% sort of electron donor, right? And then here's sort of like at 50%, or I should say 50-50, let's do it that way. 50-50 donor acceptor. And over here, you're at 100% in terms of final concentrations of your electron acceptor. Or another way you could put it is that over here, you're at 100% reduced. And over here, you're 100% oxidized. Turns out if you do this and you plot this out, because of the mathematical expression there, simple logarithm, you end up with an equation that does something like this, which ought to look really, oh, that's ugly. Let's see if I can do a better job. Which ought to look pretty similar, hopefully, to what you guys remember about the Henderson-Hasselbalch equation. And in direct analogy, right here at this midpoint, right here, the inflection point, just like we saw with the Henderson-Hasselbalch equation, is right at the point of sort of that 50-50 equivalence between fully reduced and fully oxidized, right? So the Nernst equation gives us exactly that relationship we were looking for, that allows us to predict the sort of flow of electrons given the distribution of these states, and a direct way to measure it and predict those values given a measurement of standard reduction potential relative to the hydrogen electrode. Okay, now in the next video, we're going to look at a few examples, wrap a little bit of this up, and come back to this question of why it is that NADH has so much energy available in those stored electrons.